Okay, so we're going to do 2 lectures today, carboxylic acids and then derivatives. I'll try to keep these at 30 minutes each, give or take. Okay, so the carboxylic acids, of course, they are R C double bond O H. Okay. And there are several other compounds which are considered to be derivatives of carboxylic acids, and they would include the carboxylic esters, they would include acid halides, include acid halides, and I'll pick, for example, the acid chloride as an example. They include anhydrides, and they include amides. And amides, of course, can be primary, secondary, or tertiary amides. It actually also includes nitriles, and even though nitriles don't have a carbonyl group, and they look somewhat different from carboxylic acids, they are considered carboxylic acid derivatives because they are very simple reactions you can carry out to convert the acid to the nitrile, and of course backwards. But fundamentally, these carbons are all at the acid level, and so these are all considered to be derivatives of carboxylic acids. For much of the rest of the discussion, we're going to ignore the nitriles, and we're going to focus on the carboxylic acid derivatives, on the other carboxylic acid derivatives, the ones that contain carbonyl groups. And one of the first points we're going to make is to look at the relative reactivities of the carboxylic acids and the derivatives. It turns out that the most reactive of the family would be the acid halides, followed by the anhydrides, followed by the carboxylic acids, followed by the ester, followed by the amide or the amide. And what we're looking at here is the relative reactivities of these species with respect to nucleophilic reaction. The idea is, if I take a carboxylic acid derivative, RC double bond X, and X could either be Cl or carboxylate or 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 NH2, and I treat this with a nucleophile, the nucleophile will attack the carbonyl carbon, the pi bond will break. That's going to give rise to the typical tetrahedral intermediate, right, or minus nuke, and then X. And where this mechanism differs from what we've seen with aldehydes and ketones is that with the aldehyde and ketone, what would happen next is I would protonate this O, and I could, for example, convert an aldehyde to an alcohol. But in the case of the carboxylic acid and its derivative, what happens next is that we will kick out a leaving group, because unlike aldehydes and ketones, where this X was either another carbon or an H, which of course are very bad leaving groups, in the case of these compounds, your leaving groups are chloride, carboxylate, alkoxide, or NH2 minus. And certainly the chloride and the carboxylate are pretty good leaving groups. So I would kick out X minus, and that would generate the substituted species. And I think it's worth mentioning that what we've done here really then is a nucleophilic substitution. And technically the reaction is second order, and really, as I think Marie, somebody was asking in class today, that I can consider this SN2, and the answer is I can't, because SN2 conjures reactions at sp3 hybridized carbons. This carbon is an acyl carbon. And so we consider this as nucleophilic acyl substitution, because it's very different from what you'd see in normal sp3 hybridized case. Well, I think it's also worth mentioning that if you look at how this reaction compares to the reaction of an aldehyde with some nucleophile, I'm going to put H here instead, we'd have the nucleophile attack the carbon, the pi bond would break, I'd make the tetrahedral intermediate, alright, I'd make my tetrahedral intermediate, so nuke, and I'd have H here, or in the case of a ketone I'd have R. There's no leaving group here. Now I can always go backwards, I can have this come in and kick back out the nucleophile and I can go backwards, but in terms of forward progress, all that can happen next is that species would pick up a proton from some appropriate source and generate your product, which is simply the substituted carbonyl. What I would have done in essence then is I would have added H nuke across the carbonyl bond. I'm sorry, this is the wrong species. I would have added H nuke across the carbonyl. Right? So my nucleophile will be here. So I have H nuke across the carbonyl. So in the case of reactions at the aldehyde level, they react with nucleophiles to give nucleophilic addition. But at the acid level, the reaction in fact is now nucleophilic substitution. Because this intermediate, which looks very much like this one, they differ in the sense that in the case of the intermediate from aldehydes and ketones, there is no out for the system. There's no way I can lose H minus to R minus. I could, of course, go backwards, but forward progress involves proton transfer. In the case of the reaction at the acid level, forward progress involves loss or expulsion of a leaving group, a chloride carboxylate, and so this reaction is fairly facile. Well, it turns out that if I go back to the reactions of compounds at the acid level, and I look at the two reactions, which are the attack on the carbonyl and then the expulsion of X minus, it turns out that it is this reaction, the expulsion of X minus, which plays the major role in terms of defining the reactivity of the carboxylic acid derivatives. So, how does X play a role? Well, X, if I say all of these compounds are carbonyls, when X is Cl, the Cl bleeds electron density from the carbonyl carbon, making the carbon very positive, right? More positive. So the nucleophile is encouraged to attack it, and so I get a faster attack. But chloride is also a very good leaving group. And so the loss of chloride is a facile process, so this is also a fast step. The acid halide is very reactive. The carboxylate doesn't pull electrons as effectively as does the chloride, nor is it as good a leaving group, and therefore it's not as reactive as the acid halide, because both of these steps are slower. Now, if I look at it, O pulls electrons just as well as this O. The difference is in the departure, I would have to lose OH minus, which is a strong base, and OH minus therefore is not going to come off, and so I will not get nucleophilic attack of this type on carboxylic acids. So what this is telling me is that of the two steps, it is the second step, which is the departure of X minus, or the expulsion of X minus, that dictates the rate of the reaction. So the reactivity of the acid halides mirrors the leaving group ability of this fragment of the molecule. So since Cl minus is a pretty good leaving group, so better than the lot, then acid halides are the most reactive. Carboxylates, right, are resonance stabilized, and so they're good leaving groups, not as great as chloride, right, because they're stronger bases, and therefore they're good leaving groups, just not great ones. And as you go down, your leaving group becomes hydroxide, which is a strong base, alkoxide, an even stronger base, and then of course NH2 minus, which is a very, very strong base. So the relative reactivities of these acid halides mirrors the stability of the conjugate base and mirrors the leaving group ability. And since chloride is a better leaving group than carboxylate, which is a better leaving group than OH minus, better leaving group than OR minus, better leaving group than NH2 minus, right? Then the acid halide is by far the most reactive. It also is worth mentioning that the leaving group ability is tied to the basic ability. So chloride is the weakest base of the lot, amide is the strongest base of the lock. And when we did SN1, SN2, we saw that strong bases were bad leaving groups. And this is just a rehashing of that. So the acid halides, then, the reactivities go in descending order from acid halide to anhydride to acid to ester to amide. The amides are by far the least reactive with nucleophiles. It turns out there's a consequence to the relative reactivities. And the consequence is that by and large, in a single reaction, it is possible to convert a higher derivative into a lower derivative, but not the other way around. So, for example, I can convert, if I can take, let's say I have RCOCl, and then I have the anhydride, then I have the acid, which we'll have to talk about a little bit because there's some funny things with the acid. I have the ester, and then I have the amide. Well, I have to put it here. I can treat the acid halide with carboxylate, and I will do a nucleophilic substitution to make the anhydride. In other words, RCO2 minus will be my nucleophile. So RCO2 minus will attack the carbon of the acid halide, pi bond breaks, and I'll have RCO2 minus, I'll have RCO2 here. When I kick out chloride, I'll end up with the RCO2 here. In other words, I will end up with the corresponding anhydride. If I treat the acid halide, this is going to get nasty. If I treat the acid halide with water, water becomes my nucleophile and my product becomes the carboxylic acid. If I treat the acid halide with an alcohol, with an alcohol, then I will end up with the ester as my product. Right? So with an alcohol, I get the ester. And if I treat the acid halide with ammonia or an amine, I would get the amide as my product. So I can convert the higher homolog into any of the lower ones. In a similar fashion, if I were to take the anhydride and treat it with water, in other words, hydrolyze it, I could make the acid. It's not going to be as fast as the reaction with the acid halide, but it will be reasonably quick. If I took the anhydride and I treat it with the alcohol, I will get, in a reasonably slow reaction, I'll get the ester. If I take the anhydride and treat it with ammonia, I'd make the amide, and so on and so on and so on. So what happens then is the higher homolog can make the lower homolog, but also remember the reactivity of the homologs decreases as I go down the series. So I can convert the acid into the ester with an alcohol. If I treat the acid with ammonia, I'm not going to get the amide, I'm going to get the salt, right? Because acids, the carboxylic acids, tend to react by proton transfer, because that's proton transfer fastest reaction. So if I treat the carboxylic acid with ammonia, I'm not going to get the amide, I'll get the ammonium carboxylate. Now, should I heat the ammonium carboxylate, right? If I take the ammonium carboxylate, right, NH4 plus, and I heat that, what happens is I lose water, right, H2O, and I end up with the amide. Okay? So two things so far are that the higher homolog makes the lower one, and that as you go down from halide, from acyl halide to anhydride to acid to ester and to amide, the reactivities decrease. It is not simple to go from, I cannot, for example, go from the amide to anything above it. Not simply. I cannot go from the anhydride to the acid halide. In other words, if I treat the anhydride with chloride, I'm not going to get the acid halide in any reasonable yield. And there are ways around it, there are ways you can force the reaction. All right, So we know about the relative reactivities of the acid halides, and we know how we can interconvert them. I'm going to look then at specific reactions of carboxylic acids. So I'm going to look at reactions of carboxylic acids. Now, I would also probably remind you about preparations of carboxylic acids. There are lots of ways we can make carboxylic acids. And maybe I would go to look at that first. This is really just a reminder of things we've done before, but I guess that's worth it. So let's look at preparations of carboxylic acids. We met long ago. I can prepare carboxylic acid from aldehydes and primary alcohols, right, by oxidation. Right, so I can use acidified permanganate, which goes from purple to colorless, and so on and so on and so on. I can prepare them by hydrolysis of nitriles. Right, I just heat it with that. I can also prepare carboxylic acids then from their derivatives. In other words, I can take an acid halide, treat it with water. I can take an anhydride, and I'll have to, use hot water for that one. I can convert an ester, right, with H2O plus and heat. And even amides with difficulty can be hydrolyzed to make carboxylic acids. I can also make carboxylic acids from Grignard reagents reacting with carbon dioxide. Okay, and that's going to give rise to the carboxylate, which I can then simply protonate with dill acid to make the carboxylic acid. Alright, and I can also react carbonyl compounds, alkenes and alkynes with ozone followed by hydrogen peroxide, and what that will do is generate the corresponding carboxylic acid, and that makes the assumption that you have an H in this position for chemistry. And then finally, with aromatic compounds, we saw just the other day, if I treat a compound with a benzylic H, doesn't matter what's here, with acidified permanganate, I get side chain oxidation to make the corresponding, to make the corresponding benzoic acid. Okay, so there are lots of different preps for carboxylic acids. All right, so let's look then instead at reactions of carboxylic acids. All right, so reactions of carboxylic acids. Obviously, they're acidic. So they'll do stuff with litmus, turn it from blue to red. They will react with, say, bicarbonate to give rise to the salt and carbon dioxide and water. So you see effervescence. They do the same thing with carbonates. And they give rise to the carboxylate, this carbon dioxide plus water. It's not a balanced equation, but you can balance it. So you see effervescence with carboxylic acids, and either bicarbonate or with carbonate. They will also liberate hydrogen gas with electropositive metals. So I would treat this with magnesium or zinc or iron, and I would get hydrogen gas, it's not balanced again, and then the corresponding carboxylate salt, right? Either the manganese or the magnesium or the zinc and so on, or the iron carboxylate. We can also take carboxylic acids, this is reactions as acids. We can also take carboxylic acids and we could convert them to the derivatives. So again, conversion to derivatives, I can take carboxylic acids and treat them with, say, PCl5 or PCl3 or SOCl2, any of that lot, and that would make the corresponding acid halide. I can treat carboxylic acids. If I were to heat them at really high temperatures, what they would do is they would dehydrate intermolecularly and give rise to the corresponding anhydride. Now, obviously, the best way to make an anhydride is to convert the acid to the acid halide and then treat the acid halide with carboxylate. Right? That's really the best way of making it. But this other method works as well. I can convert carboxylic acids to amides, or to esters, I'm sorry. If I would treat the carboxylic acid with an alcohol in the presence of H+, usually say a dry HCl, or what is typically used is conch sulfuric acid. So I use the alcohol with trace amounts of conch sulfuric acid. And what you get is the corresponding ester. And we will talk about this reaction in a little bit. We also talked about how I can convert the species with ammonia into the corresponding ammonium salt, which can then be dehydrated on heating to give rise to the corresponding amide. But again, the best way of doing this would have been to convert the acid into the acid halide and then treat the acid halide with ammonia. The best way of doing this one, because this is actually an equilibrium, is to treat the carboxylic acid with the PCl5 and then treat the acid halide with an alcohol to make the ester. And you get really good yields with those reactions. So really the best way of converting carboxylic acids to the derivatives is to first convert to the acid halide and then do a second reaction. So let's talk about carboxylic acids being converted into esters, because that's a particularly important reaction. So conversion of carboxylic acids into esters, that normally requires the use of an alcohol, as I said, in the presence of some acid, usually conch sulfuric acid, and you end up with the ester and water. Okay. The reaction, as you notice, is reversible. And one of the more important industrial reactions is something called saponification, which actually is the reverse of this reaction. That essentially takes a carboxylic acid ester, typically a fat, right, where you have a long chain, where R is a long chain, C10, C12, C16, and you want to convert the ester, the fat, into the corresponding carboxylic acid salt. So what you make then is a corresponding sodium carboxylate, at least in this case, and that process generates what's called a soap, because a soap is just the salt, typically the sodium salt, of a long chain fatty acid. Okay, so I'm going to end this lecture now, and we'll pick up this point later on.